So in this video, I'm going to give you a very brief introduction to sequences. Now, I'm going to start by giving you a definition of what a sequence is. A sequence is a numbered or ordered list of objects or things. Now, before I get into any examples of what a sequence is, I want to kind of handle some of the misconceptions of sequences that are kind of already ingrained into things you've already learned. So the first one is probably the most common misconception, is that all sequences are numeric, as in they all involve numbers as the things that are in our list. For example, we might see a list of just numbers in order. The thing is not all sequences are numbers. We can have a list of objects, of tasks, of words. All of these things are sequences. They're just not always numeric. From there, we might also see some issues of people concerning sequences, treating them like they're functions, or assuming that they necessarily have some form of a pattern. Well, just because it's a list doesn't mean that there's necessarily some pattern to the list. And at the same time, I refer to it as a function, is that if I were to take the number 1 and plug it in, I get some number out. If I take the number 2 and I plug it in, I get some number that follows a pattern. If I plug in 3, I get the next thing in the pattern. This is not always true. I can't always have this kind of plugging in a number and getting, it following a pattern, plugging in a number and getting something out that follows that same pattern. Along this logic, the third one that kind of comes up again would be a lot of people think that sequences are supposed to be infinite all the time, and they're not. We can have a finite sequence. For example, things like a checklist is a sequence. You have to do things in a particular order, but eventually you're going to stop. You're going to be done with the task. So again, it doesn't have to be an infinite sequence. The sequence doesn't have to keep going on and on and on forever. It can just be a finite list of things. Okay, so now that I've handled those 3 misconceptions, I'm ready to start looking at some examples. So I've got 3 examples here. The first one, hopefully you guys are paying attention to, starts off with the number 1. Then it goes to 1/2, 1/6, 1/24, 1 over 120. I'm wondering if you guys can figure out what the pattern is here. I'll give you guys a second to kind of think about that. So if you notice, this first term, this first object in the list is really the number 1 over 1. And so in order to get the next term, what we're going to do is we're going to multiply the denominator by 2, and we get 1/2. Then if I take 1 over 2 and I multiply by 3, I get 1/6. Then I take 1 over 2 and I multiply the denominator by 4, I get 1 over 24. Then the next one I multiply, that should be 1 over 6, my apologies. The next one would be 1 over 24, and we multiply that by 5, we get 120. So what I'm doing is I'm taking the previous item, the previous thing in the list, and I'm multiplying the denominator by the next biggest number. So the next one that I would do is I would take 1 over 120, and I would multiply it by 6. And that should give me my next term, my next item in the list, which would be 1 over 720. All right, so notice in this case, it is following a nice big pattern. It is involving multiplication, so that's kind of nice. The next example that I have for you is actually a very special sequence. It's called the Fibonacci sequence. And it has a very special pattern. But remember, again, not all sequences are going to have patterns. I just tried to pick ones that I thought would be nice to see because they have different kinds of patterns. In this case, the Fibonacci sequence is the sum of the first 2 terms, or the previous 2 terms. So if I add 0 plus 1, I get 1, which is the third term. Then I'll add 1 plus 1 and get 2, which is the next term. The next one is 1 plus 2, which is 3. Then I'll add 2 and 3 and get 5. then 3 and 5 and get 8. Maybe you guys can think about this and see what you get next. 5 and 8. If I add those together, we should get 13. So that would be the next term in the sequence. So that's an important thing to think about is, in this case, this one involves addition. You know, different sequences are going to have patterns, or there may not be a pattern at all. This last one is also a sequence. Notice it starts off with a triangle, which has 3 corners, 3 sides. Then we go to a rectangle, which has 4 sides, 4 corners. Then we have a pentagon, which has 5 corners or 5 sides. A hexagon, which has 6 corners or 6 sides. And if you guys are thinking logically, the next one should be a heptagon, which is 7 corners or 7 sides, followed by an octagon. So if you notice, these all do have patterns. We could also use a pattern of the digits of pi. In that case, the pattern isn't so much prevalent. It's not going to be something we can see or we can describe. Because if I just write, you know, the digits of pi, 3.1415, and it keeps on going, there's really not a pattern to these digits. They don't repeat. They don't ever they don't lend themselves to repetition. And so in this case, it is a sequence, but it's not really going to follow a pattern. This one would, in fact, be an infinite sequence because it does keep going forever. So like I said, you know, we have different kinds of sequences. You know, the ones I demonstrated here, example 1, 2, and 3, have patterns. This last one, no pattern at all. So I'm going to go ahead and move on to the next bit of vocabulary, which is the definition of a term, which is oftentimes referred to as an item in the list. It has, you know, quite a few different names, but that's the basic definition of it. A term is just part of the list. It's one element, which is another word that we oftentimes will see instead of the word term. It's just representing some member of the list. So some of the symbols we have for terms are A sub 1. Now, if I pronounce this correctly, it's A sub and then the number 1. What that represents is the first term. It's the very first thing, the very first element in the sequence. Then I'll write A sub 2, which will be the second term. And then we'll do A sub 3, which I'm hoping you guys are getting, is the third term. I'm going to do one more, which is A sub n, which is also called the general term, or the nth term, okay? Now, in this case, what A sub n is representing is any member of the sequence. Okay, so it could be the first term, could be the second term, could be the third term. Usually when we use this symbol, we're trying to describe the pattern in some way. And I'm going to talk about that next. So I'm going to talk about how we can describe, in this case, again, we're talking about sequences which don't always have patterns, but I'm going to try to illuminate some of the ones that do have patterns. So the definition of explicitly defined will be sequences whose terms, whose individual elements can be written as a function of n, as in its place in the sequence. Now this n is a variable. It's another way to describe it would be the index. Again, it's just telling me which place. Is it the first term? Is it the second term? Is it the third term, the fourth or fifth or sixth? Which place is it in the sequence? Okay, so let me go ahead and show you some examples of that. So this first example, example 1, says write the first 5 terms of the sequence A sub n equals 3 to the n. Okay, so this is my explicit definition. A sub n equals 3 to the n. And if I want to find the first term, all I'm going to do is plug in 1 into this part of the formula right here, this 3 to the n. So 3 to the first is just 3, okay? And if I want to find the second term, A sub 2, we're going to plug in 2 for n, so 3 squared gives me 9. All All right. Maybe you guys can think for a second and see how you would figure out a sub 3. Okay. Well, if we're trying to find the third term, we're going to do 3 to the third, which should be 27. All right. Then I still have to do, like it said, first 5 terms. So I'm going to have to do a sub 4 and a sub 5. All right. So the next thing in the pattern should be 3 to the 4th and 3 to the 5th. And all I have to do is grab my calculator. 3 to the 4th is 81. And 3 to the 5th is 243. So those are the first 5 terms of the sequence. Now, the wonderful thing about explicit definitions is if I just want to know what a specific term is, all I have to do is plug in that number into the definition there. Just like in the next question where it says find the 10th term of the sequence. Well, I've got my explicit definition here. If I want to find the 10th term, which is a sub 10, then all I have to do is plug in a 10 every time I see an n. So we'll do -1 to the 10 plus 1 times 2 over 10. Now that's a calculator question, so -1 to the 11th. Well, since that's an odd power, it's just going to end up being a -1. And I can simplify that 2/10 into 1/5. So I'm going to have -1 times 1/5, which is -1/5. And there's my final answer. Now, hopefully this helps get across the idea of an explicit definition. Notice again that each formula has n as its only variable. Now that's kind of the key there, is n is the only variable. There's no other variables involved in this formula. Now, I will also make sure I mention n is not the only number that might be used. Sometimes people use k. It's, again, whatever this index down here is. It's just written in terms of that only one variable. And I'm going to kind of mention to you in the next example, or in the next definition, a case where this wouldn't be the way it's written. And so that's going to be when we have a definition of something that's recursively defined. Something that's recursively defined is a sequence whose terms are written as previous element. Now, a really good example of a recursively defined sequence is the Fibonacci sequence. So I'm going to flip back to show you the Fibonacci sequence again. That was example 2. Remember, what we did was we took the previous 2 terms, like the 5 and the 8, to get 13. So that's kind of how we're going to work here with this recursive definition. Is in this case, we're looking at things that are defined by previous elements. So my first example here is it says write the first 5 terms of the sequence when our definition is given like this. Now notice, in this case, we have to have something to start with, okay? Because in order to follow the recursive definition, I have to have a previous term. I have to have some place to start with. Now in this case, it tells me what the first term is. The first term is a sub 1, which is 3. Now if I want to find a sub 2, what I'm going to have to do, if you look right here at this part of the formula, it says that in order to find the next term, k plus 1, I have to take the previous term, a sub k, minus 1, and then multiply that by 2. So here's what I'm going to do. I'm going to do 2 times the previous term, which is 3 minus 1. All right, 3 minus 1 gives me 2, so I'm going to end up doing 2 times 2, which is 4. So if I want to find the third term, again, I'm going to kind of follow the same pattern. So I'm going to take 2 times the previous number, which is 4, minus 1. Now, 4 minus 1 is 3, so we're going to end up doing 2 times 3, which is 6. And if I want to find a sub 4, I'm going to have to follow, again, the same pattern. So 2 times that previous number, which is 6, minus 1. All right, 6 minus 1 is 5, so we're going to do 2 times 5, which is 10. And if I want to find the fifth term, hopefully you guys are following my pattern here. I'll give you a second. All right, so 2 times the previous term, which is 10 minus 1. Well, 10 minus 1 gives me 9. And 2 times 9 is 18. So my first 5 terms are 3, 4, 6, 10, and 18 in that order. Okay. So notice again about this definition, or about the way the sequence is written, is that we have to be given some term to start with, an initial value, and then we're going to use that value in the rest of the formula to find the subsequent terms. Now, the upside of this is that a lot more functions can be written fairly simply using recursive definitions. Recursive definitions are actually pretty nice. However, the downside of this recursive definition is that unlike when I was doing the explicit definitions, I can't just find a specific term that I want. Like I can't find the 10th term. The reason is because I'm not actually plugging in n anymore, okay? All right, so like the example 2 says, find the next term of the sequence for a sub k plus 1 equals 1/2 of a sub k squared if the previous term is 6. So I don't even know which term this is in the sequence. All I know is that the term before it is a 6, okay? So what I'm going to do is I'm just going to say that a sub n is equal to 1/2 of the previous term squared. Okay, so again, I don't know what term this is, so I'm just going to write a sub n because it could be any term. It could be the 5th term, it could be the 10th term, it could be the 20th term. I really just don't know. All I'm going to do is follow the pattern, though, is follow this definition we're given. So 6 squared is 36, and then I'm going to take half of that, which is 18. So the next term in the sequence after 6 is 18. Now, at this moment, I want you guys to sit down and summarize what you have learned from this lesson, because we've covered a lot of stuff. Okay, so we've talked about the definition of a sequence, 3 misconceptions of a sequence. We've done some examples. We've talked about what a term is and its symbols. We've talked about explicitly defined sequences and recursively defined sequences. So again, at this time, sit down and give yourself a summary of our lesson. Hope you guys have a great day.